Hi everyone. Imagine you are sending a confidential letter across a public mailing system. You would want to make sure that no one can read it, tamper with it, or even know who it's really from or going to. Exactly. In the digital world, that's what Encapsulating Security Payload, or in short, ESP, is designed to do. It protects our data as it travels across untrusted networks like the internet. Let me show you in this video what ESP does and what kind of services it provides to our day-to-day communications. Now, if you try to understand where does this ESP fit in, it is one of the core protocols within the IPSec framework. This works at the network layer. What does it do is it provides confidentiality, integrity, and authentication for IP packets. It is primarily used to encrypt and authenticate. It is optional. If you want authentication, you can implement it. If you don't want authentication, you can skip it. The data that is being transmitted over an IP network, ensuring that the sensitive information remains protected from unauthorized access or tampering. Now, what does ESP provide? I told you that ESP provides you all these things. But to categorize its services, the first thing is it does provide confidentiality. You know by now, confidentiality ensures that your sensitive information is not visible to unauthorized users or third parties. That is what confidentiality does. Now, it does provide integrity. It makes use of hash algorithms such as HMAC SHA-1, HMAC SHA-256 to verify that the data hasn't been tampered during transit. The third service being authentication. Authenticates the origin of the data to ensure it comes from a trusted source. And finally, it also does provide an anti-replay protection. It uses sequence numbers to prevent replay attacks. So this is just as a summary of the type of services that ESP provides to the traffic at the network layer, isn't it? Now, what is the packet format? ESP does have a header, and this is the usual packet format of an ESP packet format. And what are the fields that are present within this packet format? Now, let me explain to you briefly. The first field, you can see this is 32 bits in length. That this is nothing but 4 octets or 4 bytes. Let me say that 4 bytes. Now, the first field is something called as a security parameters index, SPI. It is of 32 bits in length. It uniquely identifies the security association to which this packet belongs to. Thereby, the receiver can now select the correct keys and the algorithms for processing of this packet. If you are wondering, what do you mean by a security association? In IPSec, an security association or an SA is a unidirectional logical connection that defines the security parameters such as the encryption algorithm, authentication algorithms, the key sizes that are to be used for secure communications between the two endpoints. That is what we call as a security association. This SPI is going to uniquely identify that CA under which this packet is to be processed. Okay. The next parameter is the sequence number. Once again, the sequence number is 32 bits in length, which is a monotonically increasing counter for each security association. So for every outgoing packet within the SA, this counter keeps incrementing. It is used to prevent replay attacks by rejecting packets with duplicate or out of order sequence numbers. We will see in this video how this is being performed or how the sequence number can be used to thwart the replay attacks. Next comes the payload data, or this is the field. This is your payload data field, which can be variable in length. It actually contains the data that is being protected by the ESP. In other words, this is the actual data that the packet is carrying. In transport mode, this payload data typically contains the transport layer segment. Whereas if you are working ESP in tunnel mode, this is the fully encapsulated IP packet. Don't worry, we will discuss both the operation of ESP in both the transport mode and tunnel mode, and why do we say that this completely whether it is a transport layer segment or a full IP packet. I will discuss it in this video. This field is encrypted. You can see it is being encrypted. This field is encrypted to ensure confidentiality. Now, we have completed SPI, sequence number, and the payload data. This is the actual data that it is being receiving from the transport layer. The next field is your padding field. This padding field can be of any size. It can be from 0 to 255 bytes. Why do we need padding? You know that most of the encryption algorithms that we use are block ciphers, and they accept plain text only in the fixed size block size. Now, the padding is added so that you can align this payload to the block size as per the requirements of the encryption algorithm. Of course, it does help you to obfuscate the true length of the payload. That is, if you want to deter traffic analysis, whether the actual size of the packet, the padding can be used to ensure that you stay protected against traffic flow analysis also. That is the padding field. The next field is something called as the padding length field and the next header field. Now, the padding length field, if you see, it is 8 bits in length, isn't it? Similarly, the next header field is also 8 bits in length. These both are 1 byte. So the padding length, what does it do is it indicates the number of bytes that are added as padding, so that the receiver can distinguish what is the original. This is the original payload, isn't it? This is the original payload data that we received from the transport layer, and these padding bits we added to ensure it falls within the block size regulations or restrictions of the encryption algorithm. So for the receiver to understand what is the actual data and what is the padding data, we use the padding length field. This enables the receiver to correctly extract the actual payload during decryption. That is the role of padding length. The next one is the next header field. This is also an 8-bit value. This specifies the type of header that follows the ESP payload. So what protocol data is being transmitted using ESP, whether it might be TCP, which has value of 6, whether it is UDP, which is 17, or even an IPv6 extension header. It allows the receiver to correctly interpret the encapsulated data. So the receiver can understand what kind of protocol data is he receiving. That is the job of the next header, which is once again 8 bits in length. Then we finally come towards the last part or the last field in the header called as integrity check value or ICV. So integrity check value, this is of variable length, an optional field used when integrity protection is enabled. As I told you, ESP does provide authentication and encryption as well. Now, if you want authentication, then this integrity check value is added to the packet. It contains a cryptographic hash like using HMAC computed over the ESP header and payload, excluding the ICV itself. Now, if you go back to the diagram, you can see that these two fields where the payload data, the padding field, pad length, and next header are all encrypted. You can see clearly it's written as encrypted. Whereas SBI, sequence number, and this entire payload data is authenticated. That means this is your integrity check value field, which is computed over the entire packet. So the ICV value ensures the data integrity and authentication. It must be a multiple of 32 bits in length. Now, there is another thing here. When you are using combined mode algorithms like AES GCM, the ICV field may be omitted since the algorithm handles both encryption and authentication internally. Now, if you are wondering what are these combined mode algorithms, let me show you. The combined mode algorithms are cryptographic algorithms that combine encryption and integrity protection into a single operation. The most commonly used examples for such kind of algorithms are the AES GCM, the Galois counter mode or the advanced encryption standard in Galois counter mode, or the AES CCM, the counter with CBC MAC mode. So these algorithms automatically verify integrity and decrypt the payload in one operation. So there's no need for a separate ICV at the end of the ESP packet. So if we do remember that the integrity check value can be omitted if you are using a combined mode algorithm. If you are not using it and if it is mentioned that it is required for the algorithm, then only then we add the integrity check value. It is an variable length field. It is not fixed length. Now, in some cases, if you know, when you are using the cryptographic algorithms, we might require something called as an initialization vector, or in some cases a nonce. If any of these is present, as it is required by most of the encryption algorithms to ensure randomness, this is added before the payload data. You can see, even before the actual payload data, we are adding the initialization value or the IV data here, depending on the algorithm used. If it is not required by the algorithm, you don't have it. But if it is required, we add it on top of the payload data. Now, there is another thing here, something called as TFC padding, optional, and it is variable in length. TFC actually stands for traffic flow confidentiality. This is nothing but it is extra padding, not just for alignment, but to obfuscate the actual packet length and prevent the traffic analysis. In other words, we are adding some extra bits to confuse the attacker regarding the length of the packet. If the attacker is doing traffic analysis and if he is able to extract information based on the length of the packet, this extra padding or the TFC padding is used so that the attacker might not get enough information regarding the length of the packet. It is added after the payload data and before the normal ESP padding field. So this is, you can see, this is the field of the TFC. These are some of the fields that are present in your ESP packet. Now moving on, ESP does provide confidentiality and integrity. So we have to discuss about the encryption and authentication algorithms. The ESP service encrypts the payload data, padding, pad length, next header fields of an ESP packet. We already discussed that, isn't it? You can see the actual payload, your padding, pad length, and the next header. So these are the fields on which the encryption is performed. Now, if the encryption algorithm requires the cryptographic synchronization data, such as the IV, it is included at the start of the payload data field. Now, if there is an IV present, it would be present here on top as a separate value. Now, do remember that the IV is not encrypted. Though it forms part of the ciphertext, it is sent in the clear. It ensures that the identical plain text blocks result in different ciphertext, enhancing security. We discussed the role of initialization vector and nonces in our earlier videos. They do play the same role here also. Okay. Now, the ICV field is optional and included only if integrity protection is enabled. That means if the communication requires authentication, only then the ICV field is added. It is computed after encryption. Please do remember this. After the encryption is performed, only then the ICV is calculated. If you are wondering why should we do that, because it does have some advantages. This allows the receivers to quickly verify the packet authenticity before decryption. It detects and discards replayed or tampered packets early, helping to mitigate DOS attacks. That means rather than performing the decryption and then verifying the authenticity of the packet, it is easy to verify its authenticity and then decide whether it is a genuine packet or not. And only if it's genuine, then you go for decryption. Because the ICV itself is not encrypted, usually a keyed integrity algorithm like HMAC must be used to ensure its authenticate. You remember HMAC, isn't it? HMAC stands for hashed MAC. So an algorithm HMAC which integrates SHA-1 or SHA-256 is generally used for calculation of ICV because it includes a key value. This approach also allows for parallel processing of packets, enabling the receiver to perform decryption and integrity verification concurrently for better performance. If we do this exactly in this way, that means you do the encryption first and then perform the hash calculation or the ICV calculation. It does allow for parallel processing of packets also, which can quicken up or which the process can be done a little bit more quicker or faster at the receiver. What does the padding field do in ESP? What is its role? We already discussed this. There are some certain advantages why we have to use or why we use padding in the ESP packet. The first one, we already discussed this. It ensures that your payload data is compliant to the regulations or the restrictions of block size of the encryption algorithm. Because most of the encryption algorithms, they require the plain text to be either a multiple of 8 or 16 bytes. This padding is used or this padding is implemented to ensure the combination of the fields meets presents that or meets that particular requirement. The second reason why we have padding is you can see in the figure that ESP mandates that the pad length and the next header fields be right aligned within a 32-bit or 4-byte boundary. You can see this is a 4-byte, which is a 32-bit boundary. And the last 2 bytes should be your pad length and the next header. They should be right aligned. So the padding ensures that the final ciphertext, this entire field, you can see it's little dotted. This is encrypted, isn't it? The encrypted data is all of this. All of these 3 fields are encrypted. So padding ensures that the final ciphertext is an integer multiple of 32 bits, maintaining proper alignment. That is one of the usage for the padding field in ESP. The final thing is, I told you about the TFC padding. Padding does extra thing or does have an extra advantage where if you add this particular padding, it will help you to obscure the actual size of the packet or the payload, making it difficult for the attackers who are performing traffic analysis to analyze the traffic pattern. So these are some of the purposes which the padding field in an ESP does provide. Okay. Now, I told you in the first starting of the video that sequence numbers are quite important, and sequence numbers does allow you to thwart replay attacks. What is a replay attack? Now, a replay attack occurs when an attacker captures a valid authenticated IP packet and resends it to a destination or to the destination at a later time. That means they will grab a packet using traffic analysis. This is a genuine packet. This is an authenticated packet with all valid credentials, and they will send it at a later time to cause an unwanted effect. Even though the packet is authentic, its duplicate delivery can cause disruptions or undesired effects in the communication or application. Just think of the fact that if you are sending login credentials to your bank website, and if an attacker grabs those credentials and just before you log out, if he can send or replay that packet again, he can gain access into your bank system or into your bank website. So to counter this, ESP uses the sequence number field as a defense mechanism. Now, sir, how does the sequence number field provide defense against such attacks? The thing is, let me explain to you what the sender does and what does happen at the receiver. When a new SA or the security association is established, the sender initializes the sequence number counter to 0. It will start at 0. For each and every packet that is sent in this particular security association, the counter keeps incrementing by 1, 0, 1, 2, 3, 4, 5, 6, like that. So the sequence number corresponds to the number of present in the packet that is being sent in this SA. And whatever the counter is placed, or whenever the counter is incremented, that particular value is placed into the sequence number field. The first packet that is sent will have a sequence number of 1. Anti-replay protection is enabled by default. So when this is active, the sender must not reuse the sequence numbers. That means if I established a security association and if I start sending packets with the sequence number of 1, I can go up to, remember, the sequence number field is 32 bits. So the maximum value that I can go is 2 power 32 minus 1, which is this number. Now, if at all the number of packets have wrapped around, sir, that means I reached the maximum number, sir, this number, what do? Then, if the maximum value is reached, the sender must terminate this security association, renew a new one, and start from 1 again. Under no circumstances, you are supposed to use the same sequence number within the same security association. Now, what does the receiver do? At the receiver side, because IP is unreliable, we all know that it's a connectionless protocol, the packets can arrive out of order, get lost, or be duplicated. To handle this, IPSec mandates that the receiver maintains a sliding window to track the sequence numbers. Sir, how does it do that? What do you mean by tracking of the sequence numbers? It's quite simple actually. We already studied about sliding windows in computer networks. Let me show you how does the receiver in IPSec maintains a sliding window to ensure that replay packets are not accepted. The first thing is you have to maintain a window of size W, which can be used to monitor the valid sequence numbers. The default window size is 64. The right edge, which is this one, represents the highest validated sequence number n. For each packet within the window that is successfully authenticated, its corresponding slot is marked as received. Now, if you are wondering, sir, what is happening? Let me tell you simply, in a simple manner. Imagine that my window size is 64, okay? And this might be the left edge, which might be 10, and this edge might be 74, just for explanation purposes. If this window is 10, it means that all the packets from 1 to 9 have been received correctly and are acknowledged. Everything is done with this 1 to 9. We are done. Now, we are going to accept only the packets numbered from 10 to 74. Okay. What happens, sir? Inbound packet processing steps. Let me take this and explain. Packet within the window and new. Now, if I have received a packet with the number 14, okay, this is a new packet within my window. Now, first I will check the authenticity of this packet. If the MAC code of the packet number 14 is okay, I check the authenticity and I know that it has been received without any tampering. I am going to simply accept the packet and put it here. Okay. Now, mark the slot in the window as received. Now you know that 14 is also received. If the arrived packet is right of the window and new, that means check the MAC. If, let us say that, if the new packet has arrived, which is to the right of the window, once again I check the MAC, it is okay, it is good. Then advance the window, so the new sequence number becomes the right edge. That means if I have received something called as 75, that means I can slide this window to this because it's already been done. 10 is done, 11 is done. Now we move this towards this side and this window moves towards this side. No, sir, why are you saying this? The name itself tells you this is the sliding window. So whenever new packets arrive, this edge keeps moving or keeps sliding to accommodate all the new packets. And this edge, the left edge, once the packets are coming in, entering in, it moves to the forward so that all these packets are now acknowledged and considered done. Mark the new slot as arrived. Now packet to the left of the window or authentication fails. That means, sir, now I received another packet with the packet number of 10. What should I do? Now you know that already the window has been moved. So now this packet 10 has fallen outside of the window limit. Isn't it? Now in that case, you discard the packet because we now know that it is a replayed packet. This event should be logged, audited, as it may indicate a replay or a tampering attempt. Now when you receive a packet that is outside the window bounds, then you should not accept it, because now we know that it already has been accepted once with the same sequence number and I now cannot accept it again. This is how the receiver can now maintain a sliding window and be able to observe any attempt using replayed packets, or you can monitor and thwart the replay attack. Okay. Now let's move on to an important concept of ESP. That means we studied until now what ESP is and how its packet is structured, what are the fields present in the packet structure, and how we can use those fields to provide the services. On top of it, ESP operates in two powerful modes, one of them being the transport mode and the other one is the tunnel mode. Both of them are designed for different security needs. Whether you are securing communications between two hosts or protecting an entire network through firewalls and gateways, ESP adapts to the situation. Or you have a particular scenario, you can implement ESP that suits that particular scenario. Let's break down when, where, and how these two modes can come into play. As I told you, ESP is going to function in two distinct modes depending on the security and network architecture requirements. The first mode is called as the transport mode, or we can also say it as host-to-host security. In this mode, encryption is applied directly between two communicating hosts. That means the two endpoints. If I'm having A and B, the communication happens between A and B. Then I can use the transport mode. In this mode, only the payload of the IP packet is encrypted and or authenticated. The original IP header remains intact and visible. That means I'm not going to change anything in the IP header. I am only going to ensure that the payload of the IP packet is encrypted and if required authenticated. When this mode is ideal, I'll tell you with diagrams, we can explain it in a better way once you see the diagram and what are the different fields that are going to be protected. This mode is ideal for secure communication between the two end systems and scenarios where both the hosts support and implement IPsec. That is when we can use the transport mode. The second mode is something called as a tunnel mode. Here, we also call it as a gateway to gateway or host to gateway security. So tunnel mode can be used when one of the endpoints or one of the communicating parties is not the endpoints. Then we can use a tunnel mode. So tunnel mode is used to establish secure tunnels between untrusted networks like the network. In a way, if A is sending a packet to B, if I want to implement it between these two, I can go for transport mode. But rather than that, if I have a firewall or a router sitting here controlling B's network, then tunnel mode is used for sending the packets between A and this device, which is firewall or router, and it takes care of the internal delivery. This is your internal delivery, and this is your external part. Okay, this here the entire original IP packet, including the header and payload, is encrypted and encapsulated within a new outer IP header. I'll tell you, sir, if the entire IP packet is encrypted, how does the routers in the between understand where to route it? I'll show you. So common use cases for this kind of tunnel mode are interconnecting entire internal network securely over the internet. Traffic from internal hosts is protected without requiring them to run IPsec. Security processing is offloaded to security gateways. There are certain advantages or benefits of going for tunnel mode, which we will discuss once we understand how tunnel mode is implemented. Okay, let me show you. Let us discuss with transport mode first. In transport mode, the ESP is used to authenticate and or encrypt the transport layer payload of an IP packet, typically a TCP, UDP, or an ICMP segment. This mode is used for end-to-end security between two hosts. Now, implementing ESP in transport mode is different for IPv4 and IPv6. It's a little bit different. Let me show you. This is the original way of implementing IPv4, isn't it? You have, this is the segment that has come from the transport layer. This is the data received from upper layers, where the transport layer has added its own header and sent to the network layer. And the network layer, usually what it does is it will add its IP header and send it across. Now, if you want to implement ESP for IPv4, what you're doing is the ESP header is placed just before the transport layer header. You can see it is going to consider this segment or this particular transport layer segment received from the upper layers as one, and it's going to encrypt. You can see the ESP header is placed just before this entire thing. The ESP trailer, which includes the padding, pad length, and the next header fields, is added after the payload. So this is your payload of your ESP packet. This is your trailer. And if required, or if you want to implement authentication, the ICV value is placed in here, ESP authentication. Now, this authentication value is calculated on all these fields, including the ESP header and the encrypted format. You can see the TSP, the TCP header, and the data or the segment is encrypted, whereas authentication or the ESP authentication field contains sharp, it does implement the ICV value, which is calculated on ESP header, TCP header, and the data and the trailer. Just like we discussed how the ESP packet looks like. This is the case with IPv4 implementation. This is ESP with IPv4. Okay. Now, what about IPv6? You can understand that ESP with IPv6, this is all, ESP is considered to an end-to-end payload and it is not processed by the intermediate routers. So what do you do, sir? This is the original IPv6 header. Once again, you have the TCP and data. You have the original IP header, and in the IPv6, you know that it does have a provision to add extra headers or extension headers, which will provide more information for the routing or processing of the packet. Now, the ESP header is inserted after. The major difference is you can see that the original IP header and hop by hop, destination, routing, fragment, these extension headers are placed before the ESP header. Whereas the destination, you can see the destination options extension header may be present before or after the ESP header. That means only this extension, which might contain information about the destination, is added after the ESP header. So a ESP header is now encapsulating or is now having the destination options extension header of IPv6, the TCP header, your data, and then the ESP trailer. Once again, it has the same thing here also, ESP authentication. If you require the authentication, then you calculate the authentication or the entire thing. The ESP header, the destination options extension header, the TCP header, and your data, and your trailer. All this information, you calculate a hash, and that hash is placed into the ESP authentication field, okay, or the ICV field. So the transport layer segment, the ESP trailer, and the destination options extension header, if it comes after the ESP header, are encrypted. Authentication, if enabled, covers the ESP header and all ciphertext. You can see there are some slight things here. This is going to indicate that all these fields are encrypted. This shows encryption. Similarly here also. So this is how ESP, or the encapsulating security payload, works in transport mode. Okay. In both the cases, the original IP header is left unchanged. It is kept in the open. The CSP header is added after the original IP header, not before it. Now, what about the tunnel mode? So once again, this is your transport mode processing. What happens, sir? At the sender, the transport layer segment and the ESP trailer are encrypted. As I told you, this is what is going to happen. This encrypted block replaces the original payload in the packet. So you got the original payload. Now we encrypted it and we replace the entire payload with this encrypted one. If required or if selected, the authentication data is also added in the ICV field. If not, no. And while transit, the intermediate routers process only the IP header. That means the intermediate routers in between, that means from A to B, if you are sending any data, and if there are any routers present in between, okay, these routers now only process this data from the original IP header only. The payload remains protected. None of these routers present in between can read what is inside this packet because the payload is encrypted. Similarly, the same case with IPv6 also. Same case. As this is encrypted, only A and B can read it, can find out what it is. No one will be able to do that. At the receiver reads the SPI, which is present in the ESP header, and then decrypts the ciphertext to recover the original transport layer segments. That means at the receiver, what will be do is it will receive this, it will read the SPI, and it will understand what to do and which algorithm used to encrypt. So it will select the appropriate decryption mechanism, and then it will decrypt these two packets, this entire segment, to take it out. Okay. Now, what happens next, sir? The benefit of using this is it provides confidentiality and optional authentication at the transport layer. The applications doesn't need to implement encryption individually. ESP takes care of all the encryption at the network layer itself. But the limitation is it still allows for traffic analysis because the original IP packet headers and the lengths are clearly visible to everyone. Because the intermediate routers are processing your IP headers, the information present in the IP headers is visible. So traffic analysis is possible. This will be changed once you start using the tunnel mode. So what is tunnel mode? So tunnel mode in IPSec is designed to encrypt the entire original packet, IP packet, providing both confidentiality and also a degree of traffic flow confidentiality. So how does it do, sir? In this mode, the ESP header is placed before the original IP packet. That means, once again, let me take the IPv4 first. This is the IPv4. Earlier in transport mode, we added it here, isn't it? The header, and we encrypted this. If you see, this entire packet is now considered as a payload, and all the contents of the original IP header are now encrypted. You have the ESP header, you have the ESP trailer, and if required, you add the ESP authentication or the ICP value. Okay, you can see this. If authentication is enabled, then the authentication data is added after the encryption. You might now get it out. Sir, if you encrypt the original IP header, how does the intermediate routers read the packet and decide where to send it? That is here. Is now encrypted. Routers on the public network would not be able to forward the packet correctly. For this purpose, what you do is, now we actually add a new IP header. You can see this is called as the outer IP header. This outer IP header includes sufficient routing information but hides the details of the original communication, thwarting traffic analysis. Remember, I told you if I want to send a packet from source A to destination B via a firewall or a router present here, now this outer IP packet will be having the information of this particular firewall but not B. Maybe the internal packet will have this, in this original IP header, it will have the destination as B. I'll show you with an example. Okay. Do remember that the main difference between transport and tunnel modes are, in the tunnel mode, the entire IP packet is now encrypted. The entire IP packet. Okay. An additional and a new header is being added to this packet, which contains different routing information to the one that is present inside the original IP header. Okay. Now let me show you how it is being done. So tunnel mode is especially used in environments where a security gateway like a firewall or a VPN appliance protects an internal network. In such setups, ESP is implemented on gateways, not individual internal hosts. Now you might have 10 or 20 systems within your network. And if I can place a firewall to safeguard that particular network, I can implement ESP on that firewall rather than implementing ESP on each one of those 20 systems that are present. This is a far better choice for me. This reduces computational load on the internal host and complexity of key management. Of course, whenever you talk about security, there is always the constraint of key management. How do you do it efficiently? How do you securely share the keys? Now, because now I'm talking about implementing ESP on a single device rather than 20 different devices, the complexity of key management also gets reduced, because keys are needed only between the gateways and not between all the hosts. That is one very good benefit of using the tunnel mode. Now, as I told you, I will be explaining it with an example. Let me take, if considering an external host A sending a packet to an internal host B via the firewall. This is the firewall. Okay. Let me assume that this is the firewall and A wants to send a packet to B through this firewall. That means B's network is protected by this firewall. What happens? Let me start with the first point, which is packet creation. External host. The external host creates an inner IP packet addressed to the internal target host. That means A sends the packet to the B. Here, the ESP header is added before this inner packet. What happens is, the original packet which is transmitted by A is now placed inside another packet, and for this packet, this is all encrypted, so nobody else on the network will be able to see what's inside. But for routers which are present in between, in order to transmit this packet to B, you are going to add another header. This is called as the outer header. The main difference here is, for this outer header, the address or the destination address will be this firewalls or F, not B. A new outer IP header is added with the firewall's address as the destination. This forms the outer IP packet. This is point number 1. Point number 2. Now this packet is being sent across the network. So the outer packet is routed across the public internet to the destination firewall. So all the routers that are present in between, what they will see is, they will see a packet that is transmitted from A to the firewall. They don't know that the destination is B. So intermediate routers process only the outer IP header and any unencrypted extension headers, if there are any, in case of IPv6. As I told you, IPv6 works a little bit differently. The third one is, this packet now reaches firewall F. What happens? The firewall receives the outer packet and processes the outer IP header. In this outer IP header, once again, you see the SPI, the security parameters index. It will read the security parameters index and will now understand for which security association does this packet belong to, and then it will select the appropriate keys and algorithms to decrypt this. It will decrypt the ciphertext, recovering this original internal IP header or IP packet. It will read it, it will check the integrity, and if everything is okay, then what it will do is, the final thing is, it will deliver this internal packet to B. So A creates a packet, it goes to ESP, it will put this packet inside another packet or outer packet and will add the destination address of the firewall or the appliance that controls the network and will transmit it in tunnel mode. and this will go towards the firewall, and only then the firewall receives it. It will open it, and it will take out the inner IP packet, will read the original destination address, and then it will forward to the original destination, which is in the internal network. That is how tunnel mode works. Coming to the end, the benefits of tunnel mode are: it encrypts the original IP packet, not just the payload. It enters the complete packet. So it prevents traffic analysis, as the original source and destination addresses are now hidden. No one will know from which this packet is going, to whom this packet is being addressed to. Now imagine if there is another firewall protecting AS network, then the ESP is implemented in that particular firewall. So none of the routers in between will now able to know that packet is, the source of the packet is A and the destination of the packet is B. They will only see two appliances or two firewalls that are communicating. That is the power of tunnel mode. So it also simplifies the host configuration, because each and every host now does not require full implementation of the ESP and does not require key management. It also improves the scalability by reducing the number of keys needed. So to summarize, ESP in transport mode encrypts only the payload of the IP packet for end-to-end host communication, while in tunnel mode it encrypts the entire IP packet and encapsulates it within a new IP header for gateway to gateway or host to gateway protection, enabling secure routing across untrusted networks. I got these two diagrams from the Starring's textbook. You can see this is the original one. This is from the application layer. It comes to the transport layer, and it comes to the IP or your network layer, and then the IPSec takes over. It will simply in transport mode will add another header here and your trailer here, and if required, you add an authentication field also, or the ICV field. Whereas in tunnel mode, once you get it, this entire packet is now being encrypted and placed inside another packet. You have a new header, the ESP header is added here, and then you have a new IP header. This is not present here. Okay, and this all the remaining stuff, all the stuff like your ESP trailer and the ESP authentication data remains the same. So this is how ESP operates in both the transport and tunnel modes. Hope you understood the concepts related to the encapsulating security payload. And in my next video, I will discuss about other concepts related to the IPSec. Till then, take care and goodbye.